Nous assistons aujourd'hui à la soutenance de thèse de doctorat LMD de mademoiselle Sherry Khawla, doctorante au laboratoire de physique, dont le thème de la thèse est Exploring the electronic and optoelectronic properties of 2D materials and microstructure in renewable energy. Devant le jury ici présent, je commence par moi-même, professeur Hakima, professeur de l'Université de Galma, Monsieur le directeur de thèse, professeur Zanet Kamel de l'Université de Galma, notre invité, l'examinateur, professeur Mohamed Ben Hamida de l'Université de Msila et le docteur Monsieur Bartati de l'Université de Galma. Mademoiselle Khawla, vous avez le temps nécessaire pour nous exposer l'essentiel de tes travaux. Vous pouvez commencer.
Merci beaucoup. First of all, I would like to welcome the jury members, my supervisor, my family, and everyone here that has helped support me. I am very grateful to the jury member for taking time to review my work and being part of this committee. I also sincerely thank my supervisor. For his guidance and support over the 3 past years. It's an honor to present my work to all of you, and I really appreciate your interest in my research. My thesis tituled Exploring the Electronic and Optoelectronic Properties of Two-Dimensional Materials and Heterostructures in Renewable Energy. This work was carried out at Galma Physics Laboratory under the supervision of Professor Zanet Kamel. Before we dive into the details of my thesis, let me outline today's presentation. First, we begin with introduction. Then, I will describe the computational details. Next, we will move on to the result and discussions. And finally, I will end this presentation with a conclusion and future research direction. For the research background, with population growth and technological advances, energy demand rises. Most of energy comes from petroleum and coal, causing pollution. This challenge has driven the search for clean, sustainable, and eco-friendly sources, such as solar, wind, and hydropower. Among this, solar energy stands out as an efficient and sustainable option that generates electricity or produces hydrogen without pollution. This energy source provides a sustainable solution for our need while preserving the planet. Our research focuses on photovoltaic and photocatalytic water splitting application for clean energy generation. Why photovoltaic and photocatalytic water splitting? Both of application utilize abundant sunlight for energy generation, reduce greenhouse gas emissions, helping combat climate change, provide sustainable electricity and hydrogen fuel for clean energy solutions, enhance efficiency with advanced materials. Those advantages make photovoltaic and photocatalytic water splitting a key factor in the transition to renewable energy. Now, let's move to the mechanism of photovoltaic and photocatalytic water splitting applications. First, Light absorption. Both of photovoltaic and photocatalytic water splitting processes start with absorption of sunlight. For this, those applications require materials with strong light absorption, especially in visible and near-infrared, to maximize the efficiency. Second, charge separation. Absorption light excites electron, creating electron-hole pairs. Efficient charge separation is the threshold that prevent recombination and enhance efficiency. 3. Electric power generation for photovoltaic. The separated charge flow through an external circuit, generating direct current electricity for direct use or storage. On the other hand, for water splitting, the third step is chemical reaction. House participate in oxygen evolution reaction, where water molecules oxidize to produce oxygen and protons H+. While the electron drive the hydrogen evolution reactions, where protons generated in oxygen evolution reaction gain electrons at photocatalysis surface, generating hydrogen. Although this application has a simple mechanism, they faces several challenges. The most common challenges between photovoltaic and photocatalytic water splitting application are: first, limited solar spectrum utilization, energy loss from electron-hole recombination. For this, our research primarily aims to overcome those challenges by product new materials with enhanced efficiency, enhance solar spectrum utilization, and reduce electron-hole recombination. Now that we outline our research objective, let's move to two-dimensional materials, an important discovery in material science with many applications. What are two-dimensional materials? Two-dimensional materials are materials with atomic scale thickness consisting of one or few layers and exhibiting electronic, optical, and mechanical properties. Graphene was the first two-dimensional material synthesized by mechanical exfoliation in 2004. Since then, many other two-dimensional materials have been discovered, such as BP, HBN, MXS, and transition metal decalcogenoid, and many other structures. Now let's look to the limitation and advantages of two-dimensional materials, starting by the limitation. Two-dimensional materials is high synthesis cost, difficulties in large-scale production. On the other hand, for the advantages, high surface area, strong light-matter interaction, high mechanical strength. Now, the two-dimensional structure studied in our work. First, graphene, the first two-dimensional materials, have a planar honeycomb structure with two atoms of carbon per unit cell and hexagonal symmetry. It is extremely strong and highly conductive. After graphene, similar two-dimensional materials such as GEC, BP, BIS emerged. They have the same structure with different atomic compositions. Second, M2X2 materials consists of group 4 elements for M and group 5 elements for X. They have a layered XMMX structure with 4 stacked layers and are stable in C2M and P6M2 space group as shown in the figure. Their unique electronic, optical, and thermoelectric properties make them suitable for various applications. Janus materials are asymmetric two-dimensional structure with different atomic composition on each side, giving them unique properties distinct from symmetric two-dimensional materials. There are some Janus materials. We note that the top and bottom side of those materials are different. The asymmetric structure of Janus materials introduce polarization. This polarization generating dipole moment that enhance their performance. For example, enhanced electron-hole separation, boosts reduction and oxidation reactions, improving water splitting, increases light absorption. Those advantages have made Janus materials a focal point in the field of photovoltaic and photocatalysis. Two-dimensional materials has been utilized in various fields such as energy, sensors, photocatalysis, optoelectronics, and optoelectronics. Now, let's move to two-dimensional van der Waals heterostructures, where combining different two-dimensional materials lead to new and improved properties. Two-dimensional van der Waals heterostructures are formed by stacking different two-dimensional materials held together by weak van der Waals forces. There are two types of two-dimensional van der Waals heterostructures. First, vertical heterostructures where layers are stacked atop of each other, and lateral heterostructures where layers are arranged side by side. The K factor in heterostructures is band alignment, which determines the electronic properties and performance. Band alignment classified into 3 types. Type 1, straddling gap with straddling gap, type 2 with straight gap, and type 3 with a drooping gap. Type 2 alignment is a threshold for photovoltaic and water splitting because it enhances electron-hole separation and improves solar energy conversion efficiency. Direct Z-scheme. Z-scheme are a subclass of type 2 band alignment heterostructures where semiconductors form or heterostructures charge transfer aligns their Fermi level, creating a built-in electric field from the semiconductor with the lower work function, semiconductor 1, to the one with the higher work function, semiconductor 2 in the figure. Open light exposure, the built-in electric field prevents electrons from relaxing into the CP of semiconductor 2 and holes from moving into the VP of semiconductor 1. Now, let's move to the second part of the presentation, computational details. This thesis uses density functional theory to model material properties. Our calculations were conducted using the Vienna-Benicio simulation package VASP with projected augmented wave pseudopotential. Structural properties and stability was performed using various methods. Exchange and correlation functional used was GGA-PPE. The dynamic stability was performed through formula calculation using density functional perturbation theory method. Thermal stability assessed via ab initio molecular dynamic simulation. Mechanical stability determined using strain-stress method. The van der Waals interaction using Beck-Janssen damping DFT-D3 with Graham dispersion correction. Electronic and optical properties was performed using hybrid functional HSE06 to accurate the band gap and optical properties prediction. For pre- and post-processing tools, VASPKit, Sumo, Vesta, and Phonopi was utilized. Now we move to the main part of our presentation, which is results and discussion. This part divides into two parts. The first part focuses on photovoltaic application of BX GEC heterostructures, while the second part addresses the water splitting activity of GESNX2 Janus and its quaternary derivative. First, theoretical study of BX GEC van der Waals heterostructures where X denote P and AS for high efficiency solar cell. Part of this work was published in RSC Advances under the title of Theoretical Insight into Z-Scheme BAS-GEC van der Waals heterostructures for high efficiency solar cell. This work was with a collaboration with Professor Luc Enrard and Dr. Mohamed Shahboun from Inamir in Belgium. The motivation behind studying BX GEC heterostructures due to the properties of their monolayers, starting by GEC monolayer. Successfully synthesized via chemical vapor deposition, exhibits a direct band gap. Properties can be attained using strategies like strain engineering. On the other hand, for the BIS monolayers, known for exceptional thermal conductivity and electronic properties, high carrier mobility and strong light absorption, BP and BAS-based heterostructures show great potential for optoelectronic photocatalysis and energy application. Another motivating factor is the potential mismatch, where the mismatch between BP and GEC is only 1.35%, and between GEC and BIS is 3.75%. Both values are below 5%, indicating suitable factor to construct those heterostructures. Can I sit down? Can I sit down? First, we examine the structural properties and stability of BX GEC heterostructures. To construct those heterostructures, a GEC monolayer was stacked atop of BX monolayer. 6 possible stacking configurations were proposed for both of BP GEC and BIS GEC systems, as shown in the figure, which presents both side and top views of the configuration. After structural relaxation and bending energy calculation, all the 6 configurations are stable energetically due to the negative values of bending energy. Stacking C for BP GEC and stacking D for BIS GEC were identified as the most stable configuration due to the highly negative bending energy. As summarized in the table, to assess the dynamic stability, full spectrum analysis, which confirmed the dynamic stability of the studied heterostructures. Thermal stability was evaluated via ab initio molecular dynamic simulation at 300 and 500 Kelvin, demonstrating minimal thermal fluctuation without structural transition, confirming their thermal stability. Additionally, mechanical stability was analyzed where the obtained C11 and C12 values satisfied the mechanical stability criteria. This result confirmed the stability of the BX-GEC heterostructures, providing a solid foundation for further investigation for their physical properties. After analysis, the structural properties and stability of BX-GEC heterostructures, we now examine the electronic properties. The band structure was calculated, and the figure presents the band character of BP-GEC and BIS-GEC, where both heterostructures are semiconductors with direct band gap. The band gap value of the BP-GEC heterostructure is 1.12 electron volt. The BIS-GEC heterostructures exhibits a band gap of 1.05 electron volt. Both heterostructures exhibit a type 2 band alignment. We also analyzed the charge transfer between monolayers using better charge analysis to understand electron movement in the heterostructures. The BP-GEC heterostructure shows a smaller charge transfer with 0.008 electrons moving from the BP monolayer to the GEC monolayer. For the BIS-GEC heterostructure, the BIS monolayer allows 0.027 electrons transferred to the GEC monolayer. Next is the work function. We calculated the work function of the monolayer. BP has the value of 5.13 electron volt, BIS 4.84 electron volt, and GEC 2.81 electron volt. We also calculate the work function of the heterostructures where the work function difference was observed between the two surfaces of the heterostructures due to their asymmetric surface composition. When BX monolayers contact GEC, electron transfer for GEC to BX due to the GEC's lower work function. This aligns the Fermi level and creates a built-in electric field from GEC to BX, enhancing charge separation and carrier dynamics. Studying electronic transfer and the effect of built-in electric field is crucial. The figure shows the band alignment and carrier migration at the BP-GEC and the BIS-GEC interfaces. Under light exposure, the electric field prevents electron relaxing from GEC to BP or BIS conduction band and the hole moving into the GEC valence band. This results in electron accumulation in GEC's conduction band and holes accumulation in BX's valence band, forming a Z-scheme charge separation in both heterostructures. Since optical properties are key to evaluate materials for solar energy application, we calculate the absorption of BX-GEC heterostructures We calculate the results show that the BX-GEC tool structure significantly enhances optical absorption compared of the monolayers. Prominent absorption peaks appear in the near-infrared, visible, and UV regions. Absorption peaks of the heterostructure reach approximately to 10 power 5 centimeter power minus 1. To evaluate the photovoltaic efficiency, the power conversion efficiency PCE of the BX-GEC heterostructures was calculated using the Sharper method following the formula. BP-GEC achieves a PCE of 23.18%, while BAS-GEC achieves 13.58%, surpassing many reported heterostructures and highlighting their potential for high-efficiency solar cell. Now, we focus on the second part of our result, theoretical study of two-dimensional Janus GESN X2 and its quaternary derivatives XGESN U, where U, X and U denote P and AS. This work was published in International Journal of Hydrogen Energy under the title Understanding the Potential of Two-Dimensional Janus GESN-X2 and its Quaternary Derivatives XGESN-U for photocatalytic overall water splitting. The motivation behind studying GESN-X2 Janus and its quaternary derivatives. First, M2X2 exhibits excellent dynamic and thermal stability. Janus materials adjust band gap and type, aiding in the electron-hole dynamics. Mechanical strain influences band gap, electronic and optical properties. Janus quaternary materials remain underexplored, making this study essential. Now, the structural properties and stability. These materials are derived from the M2X2 structures, where replacing M atom with an N atom from the same group introduce asymmetry. Using the same method, we obtain quaternary Janus monolayer such as PGESNAS and ASGESNP by substituting P and AS atoms in GESNX2. After structural relaxation, formation energy calculation confirmed their energetic stability, as shown in the table. Phonon spectrum analysis, which showed no imaginary frequencies, indicated dynamic stability. Additionally, molecular dynamic simulation at 300 Kelvin demonstrated minimal thermal fluctuation without band breaking or structural transition, confirming their thermal stability. For the electronic properties, we calculated the band structure of the GESNX2 Janus materials and their quaternary derivatives. Our studied monolayers are semiconductor, among them GESNP2 and ASGESNP are indirect semiconductor, while GESNAS2 and PGESNAS are direct semiconductors. The band gap range of 0.93 to 1.84 electron volt, as shown in the table. After examining the electronic properties, we now focus on the optical properties of the studied materials. The figure illustrates the absorption of the GESNX2 genus monolayers and their quaternary derivatives. The studied genus monolayers show remarkable absorption behavior in visible light. The absorption reaches up to 1.5 10 power 5 at around 3.2 electron volt for our ternary and quaternary genus monolayers. This result highlights the potential of those genus monolayers as excellent light absorption. After that, to assess the potential of those materials for water splitting application, we aligned the band gap edge with the redox potential of water at pH 7, and we found that all two-dimensional genus monolayers except PGESNAS have band gap positions suitable for water splitting at neutral pH, making them promising for hydrogen evolution reaction and oxygen evolution reaction in photocatalysis. The main goal of photocatalytic water splitting is to improve energy conversion efficiency. Using the Fu and Als method, we evaluate the solar to hydrogen efficiency and it's corrected. The result shown in the table highlighting the GESNAS2 as the most efficient materials, achieving 21.10%, demonstrating its strong potential for solar water splitting. Strain engineering is a common method to tame the electronic and photocatalytic properties of materials. The biaxial strain from -4% to +4% in 2% steps was applied to all materials. The figure shows the band gap variation where the table presents the natural and values of band gaps. Next, we align the band gap edge with the redox potential of water splitting at pH 7 to assess the effect of biaxial strain on photocatalytic efficiency. Monolayers capable of water splitting are marked in green. We also calculated the solar to hydrogen efficiency, and the result showed that for GESMP2 under 2% tensile strain, corrected solar to hydrogen efficiency increased from 14.27% to 82%. For the ASGESMP under -2% compressive strain, corrected solar to hydrogen efficiency improved to 10.25%. Under +2% tensile strain, corrected solar to hydrogen efficiency improved to 22.13%. We come to the conclusion of the presentation. In brief, BX-GEC heterostructures stable with type 2 band alignment, strong optical absorption, high power conversion efficiency up to 31% as Z-scheme heterostructures. On the other hand, for GESNX2 genus and its quaternary, stable with excellent visible light absorption, high solar to hydrogen efficiency, exceeding commercial benchmarks, strain engineering boosts photocatalytic performance to 22.3% solar to hydrogen efficiency. Those findings underscore the promising potential of the study's materials in advanced energy conversion technologies. Their outstanding stability, efficiency, and tunability make them highly suitable for real-world applications in photovoltaic and photocatalysis. For the future research direction, we plan to Study the hydrogen and oxygen production reactions on the surfaces of studied materials for water splitting applications. Explore and predict novel high-efficiency materials for photovoltaic application. Attempt the experimental synthesis of the studied materials to confirm theoretical predictions. And thank you for your attention.